is a video walking you through the details of how you would make a velocity time graph for a video. So you notice I've got this app here called CMV Edu. It is free on the iPhone, I believe on the Android as well. I'm going to open it up. Notice I've already got this this video loaded. This is something that I took a while ago. It's actually taken at a rodeo, and this woman is trying to ride her horse around these buckets. So I want to pause it because I want to point out a few things about this video that are really important. First of all, I've got this bucket in the middle here, and if I scan forward and scan back, notice that bucket is always in frame. I see it here when she enters, and then even when she rounds that bucket, it's still in frame. That's important because I need to make sure that I keep my reference point consistent. I'm going to set this as my 0 point so that I can measure her position from that point. And I'm going to make a bunch of measurements using that reference, and I'm going to keep that reference point exactly the same throughout the entire problem. So I'm going to make a data table here. I'm not going to take too much data, but how much data you collect is up to you. I'm going to make a clock reading column, and I'm going to make a position column to begin with. And I'm actually going to start this data collection when she enters the frame, and I'm going to measure that position on the screen. So notice like the horse's head is just appearing. If I use the right side of the container as my reference, then let's say this is, I'm going to call this direction negative just for my own convenience. So I'll call this negative 8.2 centimeters. Negative 8.2 centimeters at 3.0 seconds. Notice at the bottom, I've got a clock reading. I'm going to step forward, depending on like how much time my whole video takes. I could step forward like a whole second or a half a second. I'm going to step forward a half a second until this says 3.5, and then I'm going to measure her position again. Or actually, I'm going to use the horse's head, and now it looks like it's 5.6. So at 3.5 seconds, the position is now negative 5.6 centimeters. Then I'll step forward again. Again, this delta t is up to you for your problem. You can decide something that makes sense. I'm going to call that negative 2.9, negative 2.9, 4.0 seconds, and so on. I'm not going to collect a whole lot of data here because this is just an example, but I want to point out something that happens. This looks like it's at a position of negative 0.2, negative 0.2 for 4.5 seconds, and then at 5 seconds, she has finally passed into the positive position. I'm still using the same bucket, the same barrel as my reference point, but this time I'm measuring in this direction because the horse has passed that reference point. And when I record this value, I'm going to call that 2.2 centimeters. I'm going to stop collecting data there because it's enough for these purposes. But this is interesting position data for me. Now, if I go back and watch this, it looks like the horse may be moving at an approximately constant velocity, but then the horse definitely slows down and some interesting acceleration stuff happens. If I'm actually looking to see acceleration in my video, if I want to analyze acceleration, that horse speeding up or slowing down would probably be better. But again, this is just for the purposes to show you what's going on. My next step is going to be to actually scale these values. Obviously, the horse moved more than whatever this is, like 3 centimeters in a half a second. I'm using units of centimeters here because I'm measuring on my iPhone screen, which is obviously quite tiny. So I need to think about how I'm going to scale these measurements that I made using the actual width of a horse. Now, for this reason, it would be very useful if you're taking your own video to have a measurement of some kind in the screen already. Because here I'm stuck measuring the length of the horse, saying the horse is 1 centimeter long and saying that an actual horse is, I don't know how long a horse is. Maybe it's like 2.5 meters long. So then, oops, sorry, you couldn't see that. I have a scaling factor where 1 centimeter on the screen equals 2.5 meters in real life, and I can use that actually to scale my values here. So that might look like this. If I'm trying to scale these values, 1 centimeter is to 2.5 meters as 8.2 centimeters, or even negative 8.2 centimeters, is to some value, and I would solve for that for every single one of these numbers to figure out what my actual real life position is. So 2 big takeaway points so far. I'm just going to put them as bullets because we're going to move on to one last point. Your reference point should always be on screen. Your reference point should always be on screen. And scale your quote-unquote screen measurements with real life lengths. That's what I've done here as an example of scaling. So the last point here is related to how we're going to turn this data into velocity data. Remember, the goal here is to make a velocity graph, not a position graph. And I could graph this pretty easily, and I would see, I would see position versus time data for this horse. But if I really want velocity time data for the horse, I need to do some thinking. There's lots of ways to do this actually. You can do it using calculus if you want to. You can do it using kind of like a rough measurements using the position values. I'm going to give you one example of a way to do it using your position measurements so far and turning them into average velocities. So I know that I can figure out a velocity, or an average velocity, is equal to the change in position over the change in clock reading, or displacement over time interval. If I want to know the average velocity between these two measurements, I could call that maybe 1, like time interval 1. If I want to know average velocity 1, I can calculate the displacement here. That is how much the position has changed. And it looks like it has gone from 8 to 5. I don't know, that's like 2 point, I'm going to get this wrong. But we can just do it out. XF minus XI over delta T equals, notice I'm being really careful here so I don't make a mistake, but so the final position here would be negative 5.6 minus negative 8.2 over the delta T, which is going to be 0.5 seconds from 3 to 3.5, and then negative 5.6 plus 8.2 would be 2.6. If I got that wrong, you can tell me, but 2.6 centimeters divided by 0.5 seconds is my average velocity here. I do that calculation, and it comes out to be some number of centimeters per second. That would be a third entry in my data table to say the average velocity between 3 and 3.5 is whatever that number is down here. So I could put that up here as my average velocity. Notice it's not actually an average velocity for 3.0 or 3.5. It would be halfway in between. The average velocity applies to like like the entire time interval here. But if I really wanted to graph this, I'm not going to be super picky about it, but you could do 3.0. That would technically be wrong, but it would be close enough that we could use it. 3.25 would probably be the most accurate value there. But again, the goal, if our goal here is to get a sketchable velocity time graph, you can use average velocities here and get some points that then lets you figure out what the slope of your velocity is, which will give you an acceleration. Last point here, I said this before, but I'll make it again. You want to make sure that you're actually analyzing a situation that shows acceleration. This situation that I actually collected data over doesn't show acceleration until the horse slows down. So noticing that and choosing a situation accordingly, you might even want to create a situation in the lab environment so that you're looking at something that's easy to analyze, will make your life easier down the road.